Welcome to my lesson on gears. First, let's talk about how a gear came about. Gears basically are wheels whereby someone figured out how to put teeth around the wheel so that two wheels could join, or we call it mesh, together. And gears are very useful in simple machines because we can slow down or speed up how fast they go. We can get a force advantage out of a wheel. We call that torque. Or we could simply just change the direction of a force. So here are some examples of some different gears. This is called a bevel gear. This is called a rack gear. This is a worm gear. And these ones which are used most often are called spur gears. When gears mesh together, certain things can happen. We call it a gear train when they are joined together and they turn. This would be a simple gear train with just two gears. This would be a complicated compound gear train. When two bevel gears go like this, we call it a miter gear. And when a spur gear connects to change rotary motion to a different direction with a worm gear, it's called a worm gear. So that down there, that's a worm gear. Let's talk about gear rotations. When two gears mesh together, one thing we should notice is they will always spin opposite to each other. So this gear is spinning clockwise. The gear next to it will always spin counterclockwise. So notice this one goes counterclockwise. This one will always go clockwise. The one beside it will go counterclockwise again. So when two or more gears rotate beside each other, they will go in opposite direction. And we can see this in our animation. Let's talk about some important terms. When it comes to terminology, the driving gear is always the one that has the original applied force. Now that could be a handheld crank, or it could be a belt attached to a motor somewhere. But the gear that gets the original applied force, we call the driving gear. And the gears can be many. The gears that spin as a result, we call the follower gears or the driven gear. Here are two gears. Notice this gear is turning this way, clockwise. Therefore, the other gear will turn opposite direction, counterclockwise. We can change the sizes of gears, and that can give us either a speed advantage, which means that the gear will speed up, or a torque or force advantage. So let's talk about that. Gears have teeth, and counting the number of teeth can tell us a lot about what's happening to the gear. Let's say this big gear is the one I'm cranking, or I attach a belt to it, a motor here, and the motor spins this gear. Okay. So here's my belt with the motor, and it's spinning this gear, or I use a hand to spin it. If we mark the gear and watch it spin, one turn here causes this one to spin way more times. So this one, in essence, is spinning faster because it's got a smaller diameter. How much faster? Well, we can count the number of teeth. There are 24 teeth on this one and only 12 on this one. So for every one turn the big gear makes, the little gear is going to make 2 turns according to the number of teeth. So this little gear is spinning twice as fast. So we could speed up rotary motion this way. If the gears are the same size, like this picture, there's no speed advantage or nor torque advantage. We're just changing rotary motion. We'd say that that's the only advantage. Okay, let's change our motor and let's put a belt and a motor on the small gear, which means now this one is the driving gear. This one is the driving gear. It gets the original force. And this one is the driven gear, or the follower. What will happen now? Well, we know the following. If there are 14 teeth on the driving and 28 teeth on the driven, what's going to happen is the following. For every one turn this one makes, the little one that we're spinning has to go 2 times as much. So we're actually spinning this one twice for every one turn here. But what'll happen is this gear will have more force to it. It will have what's called torque, more power. And that would be the advantage of putting the little gear as our applied force and the big gear as the follower. How much torque? Well, twice. So if I applied 10 newtons of force to this gear would have 20 newtons of force. Double, based on the number of teeth. So let's talk about this again. One way gears are useful is if we put the effort or applied force on the big gear, we can speed up rotary motion on the little gear. How do we find that? Take the number of teeth. So if this gear has 24 teeth and this gear has 12, then it's a 1-to-2 ratio. 1 spin on this one, 2 spins on this one. So we double the rotary motion. So let's say this big gear was spinning at 100 RPM. How much would the little gear be spinning? 200 RPM, or twice as much. Let's just look at a few other gears. So there, we talked about bevel gears. We'll get into wheel and axles, but if we separate gears apart, like on a bike, and attach a chain to it, we can do certain things. So let's look at gears on a bike. One thing you'll notice right away now is when we pull two gears apart and attach a chain, they now spin in the same direction if you watch the arrows. So now the gears are spinning in the same direction. Let's say here's our pedal right here. So now this, if we put our pedal here, this is the driving gear. And this still becomes the follower or the driven gear. Driven. Now let's talk about gears on a bike. First gear on a bike versus say a high gear like a 10th gear. First gear versus 10th gear. First gear, what do we know? It's easy to pedal. We usually use it to go up hills. 10th gear on a bike, however, it's hard to pedal at first, but once we get going, we can get lots of speed. So let's think about where our chain would be on the front if we were in first gear. Well, our chain would be on the big gear at the front and it would be hooked to the little gear at the back. However, if we were biking in high gear, we'd put the chain on the little gear or sprocket at the front and the big gear at the back for a high gear on our bike. So speed advantage versus force advantage. Let's look at a quick little clip about gears before we end.
possible uses for the wheel. We call a toothed wheel a gear. This video will demonstrate how gears can be used to change the direction and speed of their rotation, and how combining different sized gears can increase the amount of force exerted at the rim of the gears. We'll also compare the speed and distance covered by two different sized rolling wheels. And we'll gain a better understanding of how gears and wheels, working together, are what keeps our world in motion. This example shows how gears change the direction of rotation. When the teeth of these two equally sized gears are meshed together, the gears rotate at the same speed, but in opposite directions. Teeth from the clockwise turning gear on the left push down on the teeth of the meshing gear on the right, causing it to turn counterclockwise. Now, these two gears are the same size, but gears can come in all different sizes. The size of a gear can be measured by its number of teeth, by its circumference, its diameter, or its radius. This gear has 12 teeth. If each tooth is 1 inch wide, then the circumference of the gear is 12 inches long. There are other accurate ways to measure the size of a gear, since we know that the circumference of a circle is pi times the diameter, and 2 pi times the radius. The circumference, the diameter, and the radius are all equally good measures of the gear size. When a gear is connected to a power source, like an electric motor or a car engine, it's called the driver gear. The gear to which it's meshed is called the driven gear. In this case, the red 12-tooth gear on the left is the driver gear, and the yellow 24-tooth gear on the right is the driven gear. Because the yellow gear is twice as large as the red gear and has twice as many teeth, it rotates at only half the speed of the 12-tooth driver gear. Since the red driver gear has only half as many teeth as the yellow driven gear, the driver gear must make 2 revolutions to every 1 revolution of the driven gear. If the driver gear is turning at the rate of 10 revolutions per minute, the driven gear will turn at only 5 revolutions per minute. The ratio of the number of revolutions of the driver gear to the number of revolutions of the driven gear is called the gear ratio. Since the 12-tooth red driver gear must rotate twice for every 1 revolution of the 24-tooth yellow driven gear, this represents a 2-to-1 gear ratio. The larger the gear ratio, the slower the driven gear will turn in relation to the driver gear speed. The gear ratio can be changed by changing the size of the gears. In this example, the blue gear with 36 teeth is 3 times larger than the red gear. This gear ratio is 3-to-1. If we want the blue gear to rotate in the same direction as the red gear, we can add an additional gear. Now, this is called a gear train. This gear train consists of 12-tooth, 24-tooth, and 36-tooth gears on 3 axles. As before, the small gear on the left turns twice for each turn of the middle gear, for a 2-to-1 gear ratio. The middle gear turns 1.5 times for each turn of the blue gear on the right, giving a 1.5 gear ratio between the yellow and blue gears. Multiplying the 2 gear ratios together, 2 times 1.5 gives the same 3-to-1 gear ratio as when the red gear meshed directly with the blue gear. So the addition of the yellow gear did not affect the gear ratio, only the direction the blue gear rotates. If direction didn't matter, the yellow gear would be unnecessary. Because gear friction reduces power, engineers never use more gears than are needed. We could get larger gear ratios by